Okay, so we're looking at finishing up Chapter 9 right now, and then we'll probably have a test next week. I'm guessing we'll just put it on Thursday, although I know Sarah's got a couple tests on Thursday. Does Wednesday help at all? Because Tuesday's too early. You don't have any feedback. Well, I know. She does it all the time. That way she has easy days. I do that sometimes too, if I can. No, I know. It's just convenient too. So, well, that's how I do it too, if I can. I mean, it's nice when you know that all I have to do today is grade tests and just sit there and stare at students. I know. Okay, so what we've been looking at is chemical reactions where we have Jess. What have we been looking at? That's what I thought. Chemical reactions where we'd have A plus B goes to C plus D. And we've been balancing them. And then, so like if I have 2A and maybe I make 3C and I need 5B or something like that. And what we looked at last time is how I can take, if I'm given grams of A and grams of B, that I can calculate a limiting reactant. I can calculate the excess reactant left over. I can calculate the percent yield. I can calculate the amount of each product made. And I think that's about all we can calculate with that so far. Now, notice that our starting point has always been either we're just given enough, or we're given either grams of A or grams of B and we can skip the limiting reactant and it's just like a conversion problem, or we have grams of A and grams of B and we have to do a limiting reactant calculations. But notice that in both cases we start with mass. And that works good for maybe 25% of the reactions we do, meaning we'll actually weigh out a specific amount of compound. Like in the titrations lab, we're weighing out the amount of KHP. The other half of the time, we use solutions. And so what we have to come up with is a way to think about solutions. And see, solutions we start with, for instance, milliliters of A and milliliters of B. And our goal is still the same, meaning we still want to be able to calculate things like, limiting reactant, although in these reactions it's usually not the major point of it. We want to be able to calculate the excess reactant and things like that. The question is how are we going to do that? How are we going to get from milliliters to moles? Because we usually need to know moles. And so we talked about it a little bit yesterday. That's that new unit that we introduced, and that's molarity. And it simply stands for moles of solute. And solute is just a fancy way of saying the solid that's dissolved in the liquid, all over liters of solution. And since we make things with H2O most of the time, it's just, water. And so we kind of abbreviate that as mole per liter, or capital M stands for molarity. And if you can keep this in your mind to a certain extent, then what you'll find is that the problems we're doing today are very similar to the problems that we did the last couple days. And that's that basically molarity is the solution equivalent of molecular weight for solids. So here we're thinking in terms of volume, here we're thinking in terms of grams. If you can kind of realize that anywhere where you would normally think about using a molecular weight, instead we'll use molarity, then these problems will kind of make sense and they'll flow naturally from what we did yesterday. If you think of it as something brand new, then it's just one more thing to memorize. So try to associate it with the concept of molecular weight. Yes? Liters of solution? Yeah, SOLN is the shorthand for solution. Sorry.
Okay. No, I'm sorry. I was trying to figure it out, but I was like, I don't know.
No, it makes sense. The one that really bugs me is the chapter where you have to talk about solute. solvent, and solution. They all abbreviate SOL. I mean, who the heck comes up with 3 words to describe 3 different things that all have the same abbreviation, and then you have to use them in the same lecture? It kills me. I have to write all those words out. It's horrible. I know, you feel my pain. So the nice thing about molarity is it's actually easier than molecular weight. Because for molecular weight, you have to add up the molecular weights of all the elements in the formula. For molarity, 9 times out of 10, you're just given it probably 9 out of 10 times. And then very rarely do you actually have to calculate it. Maybe you calculate it 1 out of 10. And even the calculation part of it is pretty easy. So I personally prefer molarity questions over molecular weight questions because, to be honest, they're less work. They're easier in the aspect of, and see, I shouldn't use the word easier. They're equally hard. I guess they're less work, so they're less tedious to me. So every bottle that you see in my lab is labeled as having a molarity with it, right? Meaning you see in lab, the things might be 0.1 molar or 3 molar or 6 molar. Well, that's simply telling me how many moles of my substance I had dissolved in how many liters. So let's look at how we could make a solution like that. Making a solution. So the question is basically that I have 50.0 grams of sodium hydroxide added to 450 milliliters of water. What is the molarity of the solution? Meaning in Jay's lab, here's Jay's lovely looking bottle. What does that bottle say? Molar NaOH. And we'll put a cap on it too. Be in awe of my drawing skills. Is anyone here an artist? Can sketch things? I had one girl, man, she could sketch like the bejesus. In class, she drew me a dragon.
Do we need to draw that bottle?
No.
Okay.
That's just me being silly and waiting for you guys to catch up. So, one of the things for these types of problems when they're new to you, you want to kind of look at them in terms of what information do you have. Meaning you've got 50.0 grams of sodium hydroxide, and you've got 450.0 milliliters of water. And then what do I want? Well, you want molarity, right? And one thing I should point out is that we never actually write molarity in a problem. Meaning it can be in the answer, it can be in the question, but when we use it in the problem, we always write it in units of moles over liters because it's the moles or the liters parts that cancels out. So we need to start thinking about things in terms of our normal conversions and how we approached those problems way back in chapter 2 and how we've kind of been doing them lately. Notice that if my answer has to have 2 units moles over liters, what do I have to start with? I have to start with 2 things, right?
Oh, I was like, what?
So the idea is that if I've got 2 units in my answer, I've got to start with 2 units in here. Now notice that we know how to convert drove the arrow to the wrong spot. We know how to convert grams to moles, right? And we know how to convert milliliters to liters. So we really just have to do 2 conversions, and we can use that as our starting point. And so what I want you to think about when you're answering these questions, because sometimes we'll have 1 unit in our answer, sometimes we'll have 2, is that whatever number of units we have in our answer, that's pretty much where we have to have our starting point be. So here I'm going to put my 50.0 grams of NaOH and my 450.0 milliliters of H2O. And I'm going to do the grams of NaOH to moles first. And what is that really just? Yeah, that's just our molecular weight. We always know we can have molecular weight available to us if we have a chemical formula. So we're going to be lazy and we're going to say it's 40.00 grams is 1 mole of NaOH. And then if we're keeping track of our units, grams and grams cancel. And then the milliliters one, well, milliliters to liters, that's just literally, you know, a metric conversion. That's just on our cheat sheet. We know that 1 milliliter, 1 milliliter is 0.001 liters. Notice my milliliters cancel, and I'm just left with moles NaOH over liters of technically H2O. We usually just abbreviate that molarity. Plug that into our calculator. I get 2.78 and 2.78. And actually, I forgot, we really should say molar NaOH. I ran out of room, so I'll put it below. And notice that if you're keeping track of sig figs, since you should be keeping track of them in your background, you know, 3 sig figs, 4 sig figs, therefore the answer should have 3 sig figs. Oh, I know, you and sig figs, folks. Okay.
So you always keep the not like whatever you have in grams stuff in instead of molar because it's molar NaOH.
Oh yeah, we always, since we by default we assume it's in water, we generally just write molar NaOH and it's assumed that it's in water. If it was in something else, you would have to say what it was.
Okay.
But 99.999 and on the test and in every homework question, it's always in water. We rarely make up solutions not in water for the most part. So one of the things I want you guys to be comfortable with then is just, you know, making sure you're kind of good to go from chapter 2 for canceling units. So let's take a look at another type of problem. What if we say how many moles are in 315.0 milliliters of 0.25 molar NaOH? I'm not going to draw a fancy picture for this. So let's take a look at what you know, which is you know you have 315.0 milliliters, and you know that it's 0.25 molar NaOH. And of course, what do we want to eventually convert that to? Yeah, moles of NaOH. So notice that my ending thing has 1 unit, right? I want moles of NaOH. So that means that I have to start with just 1. So, but I've got 2 numbers in there to choose from. So which one should I start with? Cody, louder?
No, milliliters, I
Yeah.
just keep saying one.
I got to be honest, you can actually start with either one. Meaning the best way to do it is, I think the way that makes the most sense is to start with 315 milliliters of solution. And realize that since molarity has units of moles per liter, that really is our conversion factor that we're going to use for this problem. So if I want to go from milliliters to moles, well, molarity, or moles per liter, has both units in it, right? It has moles and it doesn't have milliliters exactly, but we're okay with converting milliliters to liters, and so that's going to be our conversion factor. You can actually start with the conversion factor if you want, and as long as your units cancel out and are in the right spot in the problem, then you're going to get the right answer. It's just going to look weird because halfway through the problem you're just going to have one number kind of sitting by itself. So we're just going to then convert our milliliters to liters. And one of the tedious parts, I guess, if I had to, like, you know, molecular weight's nice, or sucks because you have to calculate so many molecular weights. The annoying part about molarity is we're constantly switching between milliliters and liters, because for whatever reason they define molarity as moles per liter instead of moles per milliliter, which would have made more sense. So I've got milliliters and milliliters, and then I know that I have 0.25 moles of NaOH in 1 liter of that solution. So liters and liters cancel out, and oops, I guess I got to cancel it out. There we go. And so I multiply that all together, I get 0.079 moles of NaOH And for those keeping track of sig figs, which is always a good thing to do, see I've got 4 sig figs, but down here in my molarity I only have 2 sig figs, so my answer should have 2 sig figs. So again, just realize that that molarity is now a new conversion factor, and if you're given it in a problem, it converts between volume and moles, right? Or technically liters and moles. And so we always have it available. And as long as you pick a starting point that's reasonably logical, and I mean, I got to be honest, there's only 2 numbers to start from. So if you make those units cancel out, then you got it done. Okay, another variation of that problem. How many milliliters of 0.75 molar NaOH, and I'm picking on NaOH just because it's as good a thing as any. How many milliliters of 0.75 molar NaOH can be made with 125.0 grams of NaOH? So here again, I'm mixing up all the units. This actually is a problem that both combines stuff from earlier when we have to use molecular weight as a conversion factor, and now also molarity as a conversion factor, because we've got both a volume that we're requesting and a mass that we're starting with. So just realize that the tools you have to solve these problems are pretty much molecular weight and molarity, and then just your whole normal milliliters to liters type of thing, so your metric system. You've only got 3 choices or 4 things that you can really use in a problem like this. Nothing else. I always say that if you are persistent enough on a test like this, you could simply try all the various combinations of conversion factors and eventually get one where all the units cancel out and get the problem right. You may not know what you're doing, but through sheer perseverance and effort, you could actually get it. So let's take a look at what we know. We know that I have 125.0 grams of NaOH. I know that I have 0.75 molar NaOH. And I somehow want to be able to convert that to milliliters of NaOH. So again, I've got a choice of 2 starting points. Which one makes more sense? Yeah. Now, normally, can we convert grams to milliliters? Technically, if you know the density, right? Do you know the density of a sodium hydroxide solution? No. So realize that in this chapter, even though we're going between grams and milliliters quite a bit, almost never will we use density in this chapter because we'll never know the actual density to use. Instead, we have to use a combination of molecular weight, molecular weight, to go to moles, and then from moles we can use our molarity conversion factor. So we can use all the things that we've learned. Wonderful. 125.0 grams of NaOH. And also, remember, when in doubt, 99.99% of the time if you convert something to moles, it's probably the right start. So even if you didn't know kind of where to start this problem, realize that converting grams of NaOH to moles of NaOH is probably never a bad step. And we remember that it's 40.00 from before. So here I've used molecular weight. And then notice that since I want to go between moles and volume, well, that's just the definition of molarity. So I can say that 0.75 moles of NaOH is in 1 liter of solution. So here I've used my molarity conversion factor. And then, of course, since we're always stuck in liters, we know that 1 milliliter is 0.001 liters because we always are doing that conversion. And so here's just our milliliter to liter conversion that we are going to know and love and have memorized because we use it so much. And then my calculator spits out 4166.66 forever, but we should round that to 4,200 milliliters of NaOH solution because we want 2 sig figs in our answer, because again, you know, 4 sig figs, only 2 sig figs, so 2 sig figs in the answer.
We take the least.
Pretty much. I mean, because we're just doing multiplications and divisions, and so whatever number has the least sig figs probably is going to control the answer. Okay, so we're learning by example because these are the type of questions that are obviously going to show up on the test. So let's do an example where we combine using molecular weight, molarity, and the idea of limiting reactant. This will help us look, yeah, I know. This will help us kind of explore the similarities between molecular weight and molarity, and then, you know, the limiting reactant part's just extra bonus. So how many grams of NaCl can be produced from 25.0 grams of HCl and 100.0 milliliters of 2.0 molar NaOH, given the reaction HCl plus NaOH goes to NaCl plus H2O plus heat, since it's an acid-base reaction.
Stop right there.
I will just munch on my donut. See, if you bring me donuts every day, then I'll lecture nice and slow because I'll take donut breaks. Hmm? Oh, that's true.
Give me $20 every day, Jay.
If I give you $20 every day for donuts, I will be so out of shape, huge, and broke. No, I think the 5 or 6 donuts I had yesterday and then the one this morning is... I didn't have lunch, so I ate donuts for lunch.
I eat 5 donuts. I had half of one. I thought I was going to get sick.
Well, I have a tougher constitution than you.
Too much sugar.
It's from growing up in the high school system and having to eat high school food for like X number of years. It really toughens your stomach up. I can eat anything these days.
What about the cafeteria food? That's not
I can even stomach the cafeteria food here. It's not actually that bad most of the time, I think. Okay, so
eat it every day and I'll
if we kind of look at what we know, see, we're given 25 grams of HCl, but notice for the NaOH we have to be given both the 100 milliliters and the molarity. And so really we're given more information about the sodium hydroxide than the HCl because we're expected to, if we need to calculate the molecular weight of HCl, that we can go do it. But for molarity we have to be given it. And since this is a limiting reactant question, meaning we're given both of our starting materials and we're asked how much of the final material we make, we have to figure out which one we run out of first. So we really just have to do 2 problems. We're going to take our 25 grams of HCl, HCl, and convert that to grams of NaCl. And then we're going to take our 100 milliliters of NaOH and do the same thing, convert that to grams of NaCl to figure out which one is our limiting reactant, or really to figure out which one produces the least amount of sodium chloride. So one of the tricks for Chapter 9 that you can kind of learn and remember is that if you're given just one compound, it's just simply a conversion problem. And if you're given 2 compounds in the question, then 9 times out of 10 you have to figure out the limiting reactant for it. So this part should be reviewed, 25 grams of HCl. What should I convert to? Yeah, so grams of HCl per mole of HCl. And since Jay's lazy and actually is using his notes, he even knows this off the top of his head. Or, well, it's in his notes. He doesn't have this memorized. So grams to grams. So we use our molecular weight. Actually, here, we'll do this. Molecular weight. what do we always use next after molecular weight? Mole to mole ratio. So we know that 1 mole of HCl is 1 mole of NaOH. And where does that come from? Yeah, that's from the coefficients of the reaction. And I picked a nice easy reaction. It was pre-balanced. They're all 1s. And of course, we always finish it off by going the opposite direction. We say that 1 mole of NaOH is NaCl is what we're, oops, yeah, NaCl. I've been doing so much NaOH that I got. Yeah, I kind of got stuck in that NaOH rut, so I didn't notice it until I started typing the molecular weight, and I'm like, oh, that isn't the right thing. NaCl. So moles and moles cancel. Again, I used another molecular weight. And so I get 40.1 grams of NaCl. And I'll do the second calculation in another color to keep clear all the little extra annotations that I have. Oh, come on, just push the darn ink color button. So we're going to do the exact same calculation, except now we're going to start with 100 milliliters of NaOH. And so there's an extra little step in this question. We can't go straight to using kind of molecular weight or molarity because we're always going to be saying that 1 milliliter is 0.001 liters. And then, of course, now that we're in liters, we can use that molarity and we can say that we have 2.0 moles of NaOH is 1 liter of solution. So notice those first two parts are really what we would consider our molarity, whereas in the previous problem we just could go straight to molecular weight. But then notice our next step really is our mole to mole ratio, where we know that 1 mole of NaOH is 1 mole of NaCl. So here's our mole to mole. And then of course the ending is still the same. 1 mole of NaCl is 58.44 grams of NaCl. Now here we have to go to 12 grams of NaCl because, again, I only have 2 significant figures in that moles of NaOH. So you're right, because this is a limiting reactant problem, this is also our correct answer. Oops. Oh, well, you know, you should just nod your head and go, hell yeah, I know this shit. So, why does, oh, orange, whatever, I guess orange is good. So, therefore, you know, NaOH is the limiting reactant, and we can only make 12 grams of NaCl. So that's taking what we learned or when I say yesterday, we of course know J means Wednesday. Wednesday, where we converted our grams to moles, mole to mole, and then back to grams problem, and what we're learning today, which is how to use molarity as a conversion factor, and we went to grams in this case. So look for the similarities in these problems. Look for the patterns that are emerging, and also realize that worst case scenario, if you just take things that you know are true, which is basically if you're given a molar or a molarity in a problem, you can write that down, right? And if you have a compound, you can always calculate a molecular weight. You may not need to use it in every problem, obviously, but you could. And if you just take the normal conversion factors that you have and put them together so the units cancel, just by sheer trial and error, you ought to be able to come up with the right answer to a certain extent. Okay, one last kind of topic, and that's the idea of titrations. So, well, this is why normally I would like to give this lecture before we actually did the titrations in class. So we focused on yesterday in class just the physical measurements, right? And now what we're going to do is we're going to look at sort of how to do the math for the titrations. So remember, a titration is a reaction between two compounds one of which we know everything about it, which means we either know its mass or its volume plus its molarity. And then a second one, so the first one and then the second one, we only know how much reacts with the first. But the key is that at that neutralization point, we know that the concentration, for instance, if we're doing acids and bases, of the acid equals the concentration of the base. Therefore, we're allowed to use a mole-to-mole ratio. Meaning we know at that exact point in time that the acid and the base are the same concentration. So the idea is that we take something we know, mix it with something we don't know until they're exactly the same concentrations between them, at least compared to a mole-to-mole ratio, and then we can figure out what we don't need or what we don't know about the other problem. So there's three basic types of titration problems that I'm going to show you, okay? There's two that are good homework questions, and then I'll save the one that we actually do in lab for last. Is that fair enough? Actually, I don't even know why I ask you if it's fair enough. I'm doing it anyway. But it just feels so much better if you guys go, yeah, that rocks, Jay. Sounds like a great idea. We love it. Just some enthusiasm. Okay, so let's take a look at the first problem. Let's take a look at the first problem and we'll summarize at the end. So, sure, I'll take a bite of donut. And then we can have like a donut meter. Once Jay's donut is done, you can't stop him in lecture. He just goes until he runs out of steam. Me? I can think of worse things to be addicted to than donuts. Okay, so it required 250.0 milliliters of a sodium hydroxide solution to neutralize. That's a word that if you see it in a problem, 99.99% of the time you're doing a titration. 175.0 milliliters of an unknown concentration of HCl. Oh, I'm sorry, of H2SO4. Whoops. The question then is, what is the molarity of the H2SO4 solution? Now, we could, of course, I guess, instead of using NaOH and H2SO4 and stuff, this question could be something like, it required 250 milliliters of a sodium hydroxide solution to neutralize 175 milliliters of an unknown concentration of orange juice. In which case, we could figure out the, how acidic the orange juice is in a something. Or I saw someone doing an interesting experiment. I don't know if they intended to do it or not a couple days ago, but I thought, boy, we could figure this out. They took Pop-Tarts. They took, Skittles, that's the little word, and they dissolved them in their water bottle. And basically Skittles are sugar, and it looked like she dumped all the yellow ones in, so it tasted like orange juice apparently. And I was thinking, wow, we could figure out how much sugar or how acidic Skittles are, just for absolutely no reason other than we could. And I'm a chemist and I think weird shit like that. Okay.
If you dissolve them in vodka, you have flavored vodka.
The sad part is that's exactly what I said as soon as I started doing that. I'm like, that looks like it would be really good in vodka. And then, of course, someone else in class proceeded to tell me that, of course, you can do a rainbow then, and you can have one of every color and all this stuff. And I'm like, it sounds like an interesting chemistry experiment. Then they, of course, asked if we could distill alcohol in lab, and I'm like, maybe.
I asked that yesterday.
Oh, is that you too?
We can make moonshine,
Yeah, we can make moonshine.
Do that.
Seems like it's on a lot of students' minds for some reason.
Moonshine?
Okay, so let's take a look at what we know. we know that we have 250.0 milliliters of, did I really leave that out when I was saying it? 5.0 molar NaOH. I don't know how I left that out. Other than I apparently need to read my notes better. And we have 175.0 milliliters of an unknown solution of,
5.0.
yeah, so that's supposed to be a 5.0 way up there at the top. Otherwise, this problem would be impossible to solve and we wouldn't want to do it. And then the question, of course, is asking us to somehow convert that information to the molarity of the H2SO4 solution. And so remember, molarity has moles over liters. And then there's one other piece of information we technically know. I didn't necessarily give it to you, but you should always be able to write a balanced reaction for a problem like this. And this is another acid-base reaction, so of course it produces water and heat. And notice that the reason I need a balanced reaction is if I'm talking about NaOH and I'm talking about H2SO4, the only way to relate those two compounds to each other is through a balanced chemical reaction. And so, you know, it'd be like saying, you know, you're baking cookies and you've got this much flour, how many cookies do you make? Well, unless you have the recipe for the cookies, you have no idea how many cookies you make per cup of flour or anything like that. So you have to have that recipe, you have to have that balanced chemical reaction. Okay, so how do you think we start this problem? Well, I need two pieces of information to finish it, right? So I need two pieces of information to start it. So I've got three pieces of information because I've got 250, 5 molar, and 175. So notice that if I take the 175 milliliters, I should be able to convert that to liters, right? Since that's literally how much water the H2SO4 was dissolved in. And then I should be able to take and convert 250 milliliters of 5 molar NaOH to talking about moles of H2SO4. See, this is really H2SO4. Because I know that, you know, I have a mole to mole ratio that I can use. And I also know that I can get from milliliters to moles. So, I mean, there's all sorts of ways that I can do that. And so I'm going to start with both volumes that I'm mixing and write a bar problem. Now, if you start with them in the wrong order, say for instance you put the NaOH on the bottom, what you should realize really quickly is that your units won't cancel out, that your mole to mole ratio might be upside down and things like that. And sometimes I feel like I really should do a problem wrong someday just to show you how it kind of finishes wrong. But I don't know. Every time I do that in a class, it just confuses people because then they want to do it that way. So maybe what I've usually found is if you guys make the mistakes and you find your units aren't working or you can't figure out which one goes on top and bottom, then I'll kind of do that one-on-one. Otherwise, I like to show you the right way. So if we're going to do, I always like to do the top of the bar problem first, so I'm going to take that and say that 1 milliliter of my NaOH solution is 0.001 liters of NaOH. And then really what I'm doing is I'm combining that. That's going to be my molarity conversion factor to get to moles. So I've got, let's see, 5.0 moles of NaOH is 1 liter of NaOH. So milliliters, milliliters, liters, liters cancel. And then once I'm in moles of NaOH, as I've always said, the mole to mole ratio is the center of any problem. We know that 2 moles of NaOH is 1 mole of H2SO4. So moles NaOH and moles NaOH cancel. And then notice my moles of H2SO4, I'm not going to cancel that out because this is what I want, right, from up above. So that means I'm done with the top part of the bar problem. What I really need to do now is do one last conversion. I need to take and say that 1 milliliter of H2SO4 is 0.001 liters of H2SO4. And then we ran out of room, so we'll put it down here at the bottom. We get 3.6 molar H2SO4.
I have a question there.
Why is there not sodium NaOH?
Which one are you asking about? Which step
Right
in that?
the middle, on the bottom, the second part of molarity. What is the N in it?
This one right
there.
here?
No, next one to the left.
This one right
Yeah,
here?
where did N come
The big M? Or the...
Yeah,
from? N-A-N-O-H. Where did N
Oh, that's just me being silly. Sorry, I see what you mean. Yeah. I just threw an extra N in because I was probably saying and writing two different things at once, and that's confusing to me.
I guess I don't see where it's 5 moles of any of it. Am I blind? It's
5 moles
Where?
makes
Oh,
5.
into the problem?
Oh, okay. Where? I didn't see it.
So there's my 2 units I want to keep. And of course, if we look at sig figs real quick, we've got 4 sig figs, 4 sig figs, but we've only got 2 sig figs there, therefore we should have 2 sig figs in our answer. Sig figs for these problems should usually, the only place people seem to get confused on sig figs in these problems is if they forget the leading zeros and ending zeros and various things like that rules. Otherwise, it's pretty easy to count 4, 4, 2 and figure out what you want at the end. So that's one type of titration problem. Notice that I'm going from, volumes, and I'm trying to solve for molarity. The other way I can do that problem is I can be given 2 molarities in a volume and solve for the missing volume. So we'll just make this one up totally. We'll kind of use what we've got.
We're using molarity there, 5.0 M as a conversion factor. Why are we using its sig figs? Isn't it a conversion factor?
Well, it's one we're given, though, meaning it has to be one you either calculate or are given. It's not one that we're getting from somewhere else, like a table, meaning that's a piece of information being given in the problem. Meaning, if I went and handed you a bottle of sodium hydroxide and said, this is 5.0 molar sodium hydroxide, that's something that had to be calculated. That's something that isn't 100%. It's not 5.00000. It's not perfect. Okay, so if 175.0, well, I better pick different numbers. So otherwise, we might, if 200 milliliters of, say, 0.5 molar phosphoric acid neutralizes how much? Or maybe we should say how many milliliters, because we want to make the question in liters of, let's pick weird numbers, 2.5 molar sodium hydroxide. And let's make this up here 0.50 molar, so we have one more sig fig. So notice here what you know is you've got 200.0 milliliters of 0.50 molar H3PO4. And here you don't know how many milliliters of 2.5 molar NaOH you have. And what you want to know, or what the question is asking you to answer, is the milliliters of NaOH. And of course, we have a balanced reaction that goes with this. We know that 3 moles of NaOH react with 1 mole of H3PO4 to produce Na3PO4 plus 3 moles of water plus heat.
Okay,
Yes?
where the question mark is, what is that mole there? Shouldn't it be
Well, it's one sentence, so the question mark goes at the end of the sentence. It doesn't have.
No, when we say what we know.
Oh, why is this a question mark? Because we don't know it,
Why
right?
is there more?
It looks like it says.
Oh,
Oh, that's milliliter.
sorry. Nope, that's Jay's sloppy handwriting. So notice here, we only want one piece of information in our answer, milliliters of NaOH, so we only have to start with one thing. Now, which of those three things do you think is most logical to start with?
Who's what we know?
Well, I mean, you could start with any of those three values and piece it together. The most logical one, though, is to start with the 200 milliliters, because we know that molarity, unless it's actually being sort of the only intent of the question, meaning it's not even a titration question, it just says what molarity of solution do we start with, we almost never start with our conversion factor. So we're going to take 200.0 milliliters of H3PO4. Also notice, it gets tedious, and I know your hands might get tired and sore, and you'll have to do some hand exercises to limber them up, but I'm always putting like 200 milliliters of H3PO4, right? I don't just put 200 milliliters, because one of the things that's important to make sure you know is which you're talking about at what point, so that you don't accidentally put, say, your mole-to-mole ratio upside down or something else. So always make sure you're putting that extra information. So we know that 1 milliliter is, of course, 0.001 liters. We get tired of writing that one too, I know, but we have to do it. It's just tedious, but that's okay. And so, again, our first step in any problem is to convert to moles, right? And so I'm converting to moles using my molarity conversion factor. I know that I have 0.50 moles of H3PO4 is 1 liter of H3PO4. And then, of course, after we get to molarity, or moles, we always use our mole-to-mole ratio. So we know that 1 mole of H3PO4 is 3 moles of NaOH. So moles to moles. And then our last step is almost always some sort of mirror of our first step, in that, if we're going from milliliters to milliliters on the other end, then we have to use a molarity conversion factor again. We know that we have 2.5 moles of NaOH is 1 liter of NaOH. And then, of course, to have that symmetry, we know that 0.001 liters of NaOH is 1 milliliter of NaOH. Moles, moles, liters, liters. So notice molarity, mole-to-mole, molarity, meaning there's that pattern that's continually there. And if we answer this question, which Jay made this one up, so he's got to plug it in his calculator, 200 times 0.5 times 3 divided by 2.5 is 120 milliliters of NaOH solution. And notice that because I have 2 sig figs up here in a couple places, then I have 2 sig figs in my answer. Okay, one last problem, and then we'll call it quits for today. It's the one that you have to do to finish your lab. So if you don't want me to help you finish your lab, I guess we can stop. Oh, now you want me to go on.
Sorry, I didn't know. I was like, I get it though.
Okay, so let's take a look at a question that would be from your lab. So you start.
Is it the third type of titration problem?
Exactly. And really it's like the first type of titration problem, in that you're given a volume and you want to find the molarity of the unknown solution. It's just that in our lab we started with a massive KHP, right? So we didn't start with a volume of KHP. So we start with, say, 1.250 grams of KHP required 15.25 milliliters of NaOH solution to neutralize. What is the molarity of the NaOH solution? This is the exact question that is being asked in lab, right? Meaning you go and you measure out your KHP, you titrate it with a specific volume of NaOH, and then hope that, you know, the pink color isn't too dark and you have to do it over and over and over and over again. And then you're asked to figure out the molarity of that NaOH solution. Now in the lab, there's a lot more numbers, right? Meaning, you know, you've got initial masses, initial volumes, final volumes. But in the end, those are the two pieces of information that you get to solve this question. And so, you know, notice I'm given 1.250 grams of KHP, and I'm told I've got 15.25 milliliters of NaOH. And I need to convert that to molarity, or moles of NaOH per milliliter of NaOH. And so it's very similar to that first titration problem I did, in that, you know, the milliliters of NaOH is pretty easy because we can just convert the milliliters to liters. And then the grams of KHP to moles of NaOH should be pretty easy because we know we can use a mole-to-mole ratio at some point. Now, the difference from that first problem is that in the first problem you started off with milliliters, right? So you used molarity as a conversion factor. If I'm starting out as mass, what conversion factor am I going to use? Oh, KHP. Yep, got a little bit of minor dyslexia maybe going on. Oh, moles over liters. Boy, I'm just getting sloppy. I do kind of want to be done too. And the bad part is I realize I don't know the molecular weight of KHP off the top of my head, although I think I have it memorized. So we'll probably use it. So from this, if you remember right in the lab, it's 1 mole of KHP reacts with 1 mole, here we'll do this, 1 KHP reacts with 1 NaOH. And honestly, who cares what it makes? We just need to know the mole-to-mole ratio, right? And then the other thing we need to know from lab is the molecular weight of KHP. Now here's the kicker. That was on the pre-lab question, I think. No? Gosh darn it. Oh, you have to use it on the end question then. Here's the problem. I don't remember what KHP is exactly, so I'm going to guess that it's 204 grams per mole. But I guess since we have the internet handy, we'll just do something stupid like this. And we know that the internet's a wonderful place. So I'll bet you if I Google molecular weight of KHP, it'll probably come up. Potassium hydrogen phthalate. Yep, 204.22. Yay for having useless pieces of information stuck in your head. So then the calculation that you're basically doing is you're going to start with your 1.250 grams of KHP over your 15.25 milliliters of NaOH. And we know that, again, the first thing we want to do is get things into moles. So let's convert our KHP to moles. So we know that there's 204.22 grams of KHP in 1 mole of KHP. And of course, we know that once we're in moles, we almost always use a mole-to-mole ratio. So we know that 1 mole of KHP is 1 mole of NaOH. So that's good. We've got our top part done in that we've got our moles unit. And then the bottom part is just a metric conversion. We know that.
Where do we know that? I'm sorry. There's no reaction.
Well, I just wrote it right here.
That's
I didn't write the whole reaction, but I mean, because honestly, I'm pretty sure KHP is like KHC2O something. I mean, it's got a complicated formula. It's not potassium, hydrogen, and phosphorus. Remember, KHP is an abbreviation, right? So maybe I should go and put it in quote marks since it's an abbreviation. It's not really the compound we're talking about. And then 0.001 liters. And then we're done. We plug it into our calculator, and we get 1.250 divided by 15.25 divided by 0.001. Oops, forgot the 1 in that. Whoa. Oh, I forgot the 204. I'm like, there's no way that's a good answer. And we get 0.4014 molar NaOH. Notice that I have a whole lot of sig figs because in lab, mass is 4 sig figs, usually. Volume is 4 sig figs, and so my answer has 4 sig figs. So you really can find the molarity of this solution to a very accurate degree. So, miniature summary. Because this is how I want you to start thinking about this over the weekend and how I want you to start studying for it. Realize that we have some tools, and those tools are basically molecular weight, which has units of grams per mole, molarity now, which has units of moles per liter, and then of course we've got our mole-to-mole ratios, which arguably I guess has units of moles of A over moles of B. So 2 different mole types. So we know those tools, right? We also have that flow chart. So we know that the center of almost every problem is moles of A and moles of B, and that's our mole-to-mole ratio. And then it's just a question of how we get to A, meaning whether we have to use molecular weight or molarity, and it's a question of what we ask for afterwards, whether we ask for grams and use another molecular weight, or we ask for milliliters and use a molarity. So there's a certain symmetry to all these problems. And then the other tool, or the process I want you to think about, is organize your information. You know, what I know, and then, you know, what is the question? If you have, you know, 1 unit here, you know, you have to start with something with 1 unit. If you have 2 units, like moles per liter, then you better start with, you know, two things with, or two pieces of info, I guess. Meaning, apply some logic to these questions. If you're asked to find 1 thing, start with 1 thing. You're asked to find 2 things, start with 2 things. That should get you through a lot of the problems. And then, maybe for a big summary too, we should also say that we know that, you know, if you're given 2 reactants, that problem is automatically involves finding a limiting reactant. And if you're just given 1 reactant, then that's usually just converting to one of the products. You know, there's all sorts of those little charts that I can draw too. And we'll probably have a good review session either Monday or, wait, we said the test is Wednesday? We'll probably do a good review session on Monday, lab on Tuesday, lecture on Thursday. So that's it for me, I guess. Let me shut down the recording, and you guys can ask any sort of questions you want for the next 15 minutes or so before my next class.